Welcome to homework.
So let's start with the problem. The problem given is from optics, and here we have an optical fiber. Okay, so optical fiber has one core, okay, and there will be cladding. Always the core, it will be denser, okay, and cladding is rarer. Okay, so we have been given that n1. I'll just label down whatever is given in the problem. So just 1 second. Sorry for the disturbance. Okay, I'll continue. Okay, this is the imaginary line passing through the center. Okay, so there is an incident ray, okay, at the core. Okay, so it comes like this. It is incident and it is making an angle of theta I. Okay, it enters the core. So it is coming from here. So here is rarer and this is denser, so the bending will be towards the normal. Okay, the refraction will be towards the normal, and this was our normal. Okay, so it will be towards the normal, so it goes like this is the path. Okay, and then it hits the cladding and core interface, and from there according to the figure it is reflected internally. Okay, and we have been given the core is n1 and the refractive index of cladding is n2, and we have been given n1 is equal to 1.465 and n2 is equal to 1.450. It is given that this is of silica and germanium, and this is of silica only. We need not go into that. So what we have to do is we have to find the critical angle. So we have to find theta critical, and then we have to show that sine theta I is equal to root n1 square minus n2 square. Okay, and then we have to show we have to find the value of theta I. Okay, these are the things that we have to do. So let's start. Okay, so I'll tell you the light entered at the core and air interface. Okay, so core is denser, so it was refracted towards the normal. Okay, so bending is towards the normal. It then goes to the cladding and core interface, and then it is internally reflected because this angle will be greater than C, critical angle theta critical. Okay, so I'll make the normal at this point also. Okay, so like this I'll make. Okay, so I'll take the angle over here as theta R, and this is theta C. Okay, so okay, let us for a time being you consider this as theta C. Okay, this will be something else. Okay, I'll write theta, I'll write C itself, not theta C. I'll write C. Theta C is your critical angle. Okay, okay, so when the angle over here it is greater than theta C. Okay, when it is greater than theta C, then only total internal reflection will take place. Okay, so okay, so let's start. So we have to find the theta C. Okay, theta critical is what? The critical angle. So at critical angle what happens is there will be what? Refraction along the normal. Okay, sorry, along the surface. So the angle will be 90. Okay, so this is theta C. Okay, so this is taking place at this. Okay, imagine this over here. Okay, so what we will do, using Snell's law, we will write law of refraction. We can write this is n1, this is n2. Okay, this was core and this is cladding. This is taking place at this point. Okay, so I write n1 sine theta C equal to into sine of 90. Okay, the angle refracted angle over here is actually 90 degree. Okay, so sine 90 is 1, so this becomes n1 sine theta C is equal to n2. Okay, sine theta C is I have written critical as theta c. Okay, so sine theta c is n2 by n1. So if you know the definition or formula, you can straight away use it. Okay, this is actually the derivation for it. So okay, so I'll write sine theta c is equal to n2 by n1. Okay, so over here we have n2 as how much? N2 is 1.45. Okay, n2 is 1.45 and n1 is 1.46. So I'll substitute the value 1.46. Okay, so this comes around 0.98. Okay, so I have sine theta c as 0.98. Okay, so if I need theta c, it will be sine inverse of 0.98. Okay, sine inverse of 0.98, and this comes around 78.5 degree. Okay, so we have found theta c as 78.5 degree. So let's move on to the B part. Okay, where we have to derive the what we have to derive sine this numerical aperture. This is actually numerical aperture. I'll write it over here. This is actually numerical aperture. We have to derive it. Okay, so I'll copy this figure onto that place. Okay, copy, and let's start deriving it. Okay, so it hasn't come. Okay, let's start from again. Okay, so we solved that problem. So I'll draw a condition. Okay, this is the normal. Okay, the ray is entering. We have this is n2 and this was n sorry, the core was n1. Okay, am I right? Yes, the core is n1 and the cladding is n2. Okay, so it will be incident over here, so it will bend towards the normal, and then from here it underwent TIR, total internal reflection. Okay, so this is we are assuming at C, and C is always greater than theta C. Okay, then only it will get reflected internally. Otherwise what at theta C, what happens is it is refracted along the surface. Okay, so let's start proving it, and this is theta I. Okay, so let's start proving it. Okay, so what I'll do is I'll assume n naught as the, I'll write everything, okay, as the refractive index of air. Okay, so at the air core interface. Okay, air core interface is this point. Okay, so here I'll write, okay, I forgot to write the angle over here. Let us assume it as theta r. Okay, refracted. Okay, it is refracted from the normal. Okay, so let's write the Snell's law. Okay, using Snell's law. Okay, I'll write the equation for this. So what I'll write is n naught theta I, n naught sine theta I. N naught is at this is for air medium. N naught sine theta I equals the refractive index for core is n1. So n1 sine theta r. Okay, sine theta r. This is what I can write. Okay, so I'll write sine, and we know n naught refractive index of air is 1. Okay, so this will become sine theta I equals n1 sine theta r. Okay, so what I can see is this triangle, if you can look carefully. Okay, this is this triangle. I'm taking it over here. So this angle is theta r, and this is C, and this is 90 degree. Okay, so can I write 90 plus theta r plus C as 180? Okay, so I can take this C and 180 over here. So theta r becomes 90 minus C. Okay, I have know this concept. Okay, I have what calculated theta r as 90 minus C. Okay, so I'll substitute over here. 90 is 90 degree. Okay, so sine theta I equal n1 sine theta, instead of theta r I'll put 90 minus C. Okay, if you know 90 is nothing but our pi by 2. Okay, so we know sine pi by 2 minus theta is what? Sine pi by 2 minus theta is cos theta. Okay, so we also know sine 90 minus theta is cos theta. So I'll write it, sine theta I is equal to n1 sine this will change to cos C. Okay, this is one relation that we have. Now what we'll do is we will apply the Snell's law at this point. Okay, so I'll write at this point, I'll draw it. Okay, so it is like this is the normal. and this is okay. So this is C. Okay, so I write this was N1, this was N2, this is our core, this is our cladding. Okay, so at core cladding interface I write, okay, this was C, and this is assume it at and going at 90 degree. Okay, at theta C. Okay, so I write sine sorry, I'll multiply the refractive index n1 sine C. Okay, n1 sine C equal to n2 sine 90. Okay, this will be n2 sine 90. Okay, and what I can do is sine C, I can write it as this will be 1. Okay, and I'll take n1 there, so this will become n2 by n1. So I have got this relation. Okay, and also I know okay, and what we got from the previous step is this thing. Okay, so I write it over here. I write sine theta I equal to n1 cos C. Okay, cos C. So we know what is sine C, we don't know what is cos C. So we have learned is sine square theta plus cos square theta is equal to 1. So cos square theta, can we write it like 1 minus sine square theta? Okay, and cos theta is nothing but under root 1 minus sine square theta. Okay, this is the formula that we are going to use it over here. So instead of C, we will be putting this. Okay, so this becomes I can write it as n1, okay, under root 1 minus sine square C. Okay, this is sine theta I itself. Okay, and instead of sine C, I'll substitute these values. Okay, so this becomes sine theta I equal to n1, and I'll right, this substitute this value n2 by n1 square. Okay, now I'll expand it. Okay, this becomes n1 under root, okay, denominator it will become n1 square minus n2 square upon n1 square. Okay, now what I'll do is I'll take this n1 out. Okay, so this becomes sine theta I sorry, I need not write sine theta I. I'll write n1 upon n1 under root n1 square minus n2 square. Okay, since I took this n1 square, it will come out in denominator as n1. Okay, now I'll cancel this n1 and n1. I'll use different color. Okay, I'll cancel them, so I'll get what? I'll get sine theta I is equal to under root n1 square minus n2 square. This is what we needed to prove in part B. I hope you got it. Okay, so I'll do a quick recap. Okay, we will write the using Snell's law, we will write the equation at the core and air interface, and then we will write it at the core cladding interface. So when we write at air interface, we get this relation, and when we write at core cladding interface, we get this relation. Okay, and this relation. Okay, and this thing we will substitute in equation 1. Okay, I'll name it, this is equation 1 and this was equation 2. Okay, so I'll substitute 2 in equation 1. Okay, so we substituted this and we got this relation. Okay, this was what we had to find in the second part. Okay, now this is the second part. So part 1 we have done theta critical, we have found it was 78.5. we have done sine theta, we have proved it. Now we have to find theta I. Okay, so it is simple, we will just use this formula. Okay, so moving on. So I'll write sine theta I equals under root n1 square minus n2 square, and the values have been given. N1 is the core, its refractive index is 1.465 and n2 it is 1.45. okay, so I'll do the square and I'll just substitute. Okay, this is 1.465 square minus 1.45 square. Okay, so this is 2.14 around, and this is 2.10. okay, so this is what, 0.04, and this comes out to be 0.2. so we know sine theta I is equal to 0.2. so if I need theta I, this becomes sine inverse of 0.2. okay, and this comes around 11.53. okay, so I forgot to mention one thing over here. This is nothing but this is our numerical aperture. Okay, numerical aperture that we needed to find. Okay, I forget to mention the term. So numerical aperture is the capacity to absorb the light. Okay, capacity of lens or this optical, here we are discussing about optical fiber, its capacity to absorb the light. Okay, so the light will enter, there will be acceptance cone over here, so how much amount of light it can capture, and that light will be passing through multiple reflections inside it. Okay, so that is what numerical aperture is. Okay, so we have found what is theta I. I'll write it down. We have found theta I. Okay, so these are the things, and I'll summarize once more what all things we have found. We found theta critical. Okay, and its value was 78.5 degree. I write it over here, 78.5 degree. Then we proved sine theta I equal to under root n1 square minus n2 square